Duetto, vieni qua anche tu. È come che ti tenga la mano. Esatto. Cioè, va, lo vedi che te sono finito. Okay, can you hear me? Yes, I think you can hear me. So good afternoon, everyone. As you may know, some of you know, I'm the director of the Department of Physics and Astronomy at University of Bologna. And it is really an immense pleasure to welcome here Professor Genzel on behalf of University of Bologna that invested a lot in this campus where we have a very extended platform for training in astrophysics, as you know, with the bachelor, master courses and PhD courses, and also professional master in space mission. But this is not the topic of this afternoon. It was only, let's say, great greeting from the University of Bologna. Today, it is really a very, very special day because we have the fantastic opportunity from students to staff to hear let's say, a very fascinating story where advanced technology and fundamental research meet together. We will hear about very large telescopes in the most remote places of the Earth. We will hear about adaptive optics to, let's say, beat the atmospheric turbulence, near infrared imaging to beat the interstellar extinction and to penetrate into the nucleus of our galaxy. We will hear about the Kepler's law and the application of the Kepler's law to the estimate of the mass of black hole, something that my students know very well. And then also fundamental research and fundamental physics with the black hole and much more. So I think I can stop here for this very brief greeting and welcome to you, and especially to Professor Genzel. Without any self-celebration, I want just to say, to remind that I had the pleasure to collaborate with Professor Genzel in 2006 and 2007, where I also visited for a few months his institute, and I had the pleasure to really experience this very exciting atmosphere of that place. So I'm even more excited to be here and to have the possibility to hear from Professor Genzel. So thank you very much from all of us for being here, and I really wish you a very successful, exciting, and a pleasant afternoon. Thank you.
All right. It's my turn. I am the director of the Observatory of FINAF, and also on behalf of Tiziana, which is the director of the other institute. I'm pleased to see many people here to listen the lecture of Professor Genzel. And so it's a great honor to introduce Professor Genzel, also a responsibility. So let me start with a small story. I was at the Max Planck in the 90s. There is no need to be more specific about the date. And at that time, the Rosat group, my boss was Joachim Trumper, and I was working for Rosat. And we were in the container outside the main building because there was no space, possibly a situation that we are facing now or soon, given that we are growing, which is a very good thing. And so to go to the library, because at that time you cannot Google a paper, you have to go to the library and read it and copy. I had to go through the main building, and there was a door always open with a guy with the red hairs reading papers on his office, and I was told that it was one of the infrared group, Reinhard Genzel, and I was thinking, okay, fine, I am in a different part of the group, and I never had the opportunity, or I was not smart enough to try to discuss that. Then I took a different path. I was doing X-ray astronomy most of the time, but we had chances to collaborate in vast group. And what I'd like to remark for Professor Genzel is that besides the story, the 40 years path that led to the Nobel Prize for his studies on the galactic center and the central black hole in our galaxy, he gave a very relevant contribution to different fields. Let me name just galaxy evolution and high redshift galaxies and AGN, with an approach that was, I think, the correct one, but is not easy to implement. So he had a clear idea in mind. I think he started in the late 80s to work on the galactic center. And then he devised and he developed and he built the instrument to prove his ideas. And among them, let me recall the integral field spectroscopy that led to Symphony. He also made a very relevant contribution to space mission like ISO and Herschel, and more recently on the gravity and Gravity Plus, which is going to be implemented, and also with an eye to the future with Mikado, which is going to be the infrared camera for the ELT telescope, which is going to be built in Chile. So this is an incomplete and short review of the Genzel achievements, but today we will listen about the 40-year journey and the discovery of the black hole in the center of our galaxy. Thank you very much, and please, Reinhard, the floor is yours.
Well, thank you, the two Andreas, but you didn't sing the duetto later. Right, so I'd like to invite you to a trip, a journey which I'm afraid I have to say took me a little long, 40 years, and still ongoing, and I'm afraid still ongoing for probably beyond my career, and that is to test something which 107 years ago was initially implicit and then could be found mathematically explicitly in the field equation of Albert Einstein's. And that is a so-called black hole. I'll explain a little bit what that is and how one might find it. And then, of course, the question is, how would you prove it? As an experimentalist, as a physicist, not just saying that you have it, but actually having evidence which is convincing. Now, this kind of project you don't do in one afternoon, and you need a lot of good people to help executing it. And in my case, if this machine will work, it's frozen. Thank you. Wonderful. So here are a few of the many fantastic colleagues and friends and people from throughout Europe who have joined me on this endeavor of working, building instruments, then doing the science, doing the theoretical explanations, and so forth. And so it is in some parts of science that you can't expect to be done in one afternoon. And so that's why it's a journey of 40 years. As I said, general relativity more than 100 years ago was basically a new way to describe the action of masses onto masses. And of course, in Kepler and Newton, that was a force, the force of gravity. And that was sufficient to understand, for instance, the solar system and the Keplerian orbits in the solar system. The fact that when the mass is dominated by a single central object, the surrounding planets have orbital speeds which decrease with distance from the central object, like 1/square root of distance. So that we knew, but there was one, shall we say, big hole in there. That theory was not easily or not at all applicable to very fast motions. And by the late 1890s, it was clear from experiments by Michelson and Morley that indeed the speed of light was the maximum speed limit in our universe, despite what you hear in various science fiction novels. It's the maximum speed, and that gravity also influences photons, as we would say nowadays. It's interesting to say, actually, during Newton's time, that was also explicitly discussed by others, that light is not just a light ray which passes by the sun without any interaction, but actually were corpuscles which would be affected by gravity. But anyhow, the 19th century and Maxwell's formulation of electromagnetic radiation clearly pushed the effect of radiation as a light phenomenon, a wave phenomenon, to the fore. And so with Einstein, we are in a situation that all of a sudden photons see gravity. And that has important and easy to understand ramifications. Consider the sun or any other object which has a mass and a size. And then according to Newton, you can calculate what a rocket would have to have as a speed in order to escape from the surface to infinity. That's just the mass over the size times the gravitational constant and the square root of that. That's that speed. And if you calculate that for the sun, you get to 600 kilometers per second. If you do it for the Earth, it's 11 kilometers per second. That's exactly what we all nowadays, modern humans, know, because we see rockets take off from Earth. 600 kilometers per second. Now that velocity, as I said, depends on the mass, but it also depends on the size. So if we, in our thoughts, create another sun, same mass, but much smaller, say 3 kilometers in size, you can calculate again, gm over r square root, and you'll find that this is 300,000 kilometers per second. What is 300,000 kilometers per second? That's the speed of light. So if I make it 1 millimeter smaller, then at least mathematically, that speed is greater than the speed of light. And that cannot be. So there you go. The conclusion must be mathematically that an object, if it's of that mass, within this radius of 3 kilometers, cannot have light escape. So you have a so-called event horizon. But how could you see such an object? Obviously, it cannot radiate, but can you see it in any other way? Well, yeah, through gravitation, through the interaction between the mass and other masses. So for instance, if said object would be in a solar system with the same planets of our planets, well, then the planets would, to first order, move in the same orbits as around the sun, the same Keplerian laws. And the Keplerian laws tell you, I mentioned that the sun dominates by mass. And from the speeds, which you can measure the mass of the sun. So in principle, therefore, you have a thought experiment, how you see a black hole. Now, how are you sure it's a black hole? Well, you would have to have a planet there in this picture, which is very, very close to the event horizon. Not inside, that is not possible, but just outside. So that's the description of what we as physicists would have to do. And of course, you can imagine that latter part is the problem, to get close enough to any object. As you will see, to measure them masses through motions of surrounding bound objects is possible, and we have now several ways of doing this. But the trick is to come close enough that at least mathematically you can exclude and perhaps even physically show that the object must be a black hole. Now that's the mathematics, if you like, in the background. And so general relativity was for many years between the invention and later on sort of privilege of the mathematicians in the university buildings. the physicists, yeah, to some extent. There were some in the 1950s who did the first experiments on Earth to show that some of the effects shown by Albert Einstein were there. Of course, there was the bending of the light and the perihale motion of the Mercury, which was seen from the beginning, but that was about it. Certainly black holes as such were not seen. But then in the 1960s, two things happened. One is the X-ray astronomy community had their first satellites, which were sensitive enough to see distant sources of X-ray radiation. And they found interesting objects, which were binaries with one visible star and another one which was not visible in the optical, but in the X-rays. Very intense X-ray sources. And if you looked at the motions of that system, you would conclude in some cases that the mass of the invisible object was 10 solar masses or so. And invisible meant, of course, very compact. And so that was, if you like, the first sighting of what we now would call a stellar mass black hole. We are much further than that now, because in the same way as what I will tell you about the center of our Milky Way, there's another technique to sense masses, and that's gravitational waves. Very important technique. I'll come back to that at the end of the talk. In any case, a second way was the discovery of the so-called quasars. Radio astronomers in Cambridge and elsewhere were scouting the sky for their for emission from radio sources, and they found a number of very bright radio sources, which were not all that bright or not at all bright in the optical domain. And so one of them was this object there, 3C273, discovered in Cambridge, and that object was quite interestingly a very faint 16th magnitude optical star, therefore obviously compact, highly variable in the radio, and therefore the size obviously very small. And then Martin Schmidt made the critical experiment. He took the Palomar telescope and took a spectrum of this object and found that in the spectrum there were emission lines due to hydrogen, helium, oxygen, and so forth, very well-known emission lines, but all of them redshifted by 16% relative to the laboratory frame. Well, how could that be? Well, of course, at that time already, for 30 years, it was known that the universe as a whole is expanding. And then in an expanding universe, if you look at a distant object, which is moving away from you, then the red shift is proportional to the distance. So if you apply that to this 16%, you find that this object would have to be 2.4 billion light years away. Light would take 2.4 billion years, which is a significant fraction of the age of the universe. A sensation at the time, because at that time, the universe was more known on scales of millions of light years, but not billions. But if it's that far away, then this meager little light source, especially at the radio waves, must be very luminous locally. You can calculate that, of course, and when you do so, you find that this object, which one calls a quasar, quasi-stellar radio source, has an equivalent luminosity of about 1,000 times that of the Milky Way. 1,000 times that of the entire Milky Way with its 1,000 billion stars. Wow. So is that a concentration of stars? Not really, people found. When they looked closer, it also produced X-rays and highly variable emission. So-called radio jets were discovered, plasma expelled from the center of these objects at near the speed of light. That doesn't look like a stellar cluster, so to speak. And so the idea was, what could you, as a theorist, think of which would produce so much energy? And here comes the paradoxon, black hole. Heck, how can that work? Well, yeah, I told you that, of course, light cannot escape from within the event horizon, but from outside it can. From outside it can. And so if you have a situation where you have a black hole and then you have gas falling in, say, in a plane so that the gas sort of spirals inward towards the black hole and then disappears eventually, then on the way, during the in-spiral, it gets hotter and hotter as gravitational energy on the way gets converted into radiation. And here comes the trick. The equivalent energy which can be released near the event horizon is huge. Depending on the rotation of the black hole, it can be up to 40% of the rest mass energy mc squared. Fusion in stars, which light up stars in the Milky Way, is a fraction of a percent. So that's 1,000 times more efficient, theoretically at least, radiation source than stars. So that was the idea of a number of famous theorists, Donald Lindenbell, Martin Rees, Rashid Sanyayev, Blandford, and others. And over the years became the leading theory. But is it true? In the sciences, everyone is free to say whatever they like, but they have to contend that their proposal has to be tested and shown to be correct. All right, so that's the situation where the galactic center came in. Why the galactic center? Because the galactic center is close by. And Lindenbell and Rees had argued, well, if you look at these distant quasars, it's going to be difficult to measure motions in resolved fashion. We can do that now, but not then. I apologize for the motion here. That's not the movie, that's the interaction between computers as we know it. So the galactic center is close, and Lindenbell and Rees proposed in 71 that maybe these quasars are just the tip of the iceberg of very highly accreting black holes, and maybe other galaxies also have black holes, including our own. And indeed, that's what started experiments in the galactic center, where we can look very deeply into the central region, where we can see stars, a highly dense concentration of stars, about 1 million times denser than in the environment we live in, and gas clouds, and also, and that was the important thing, a central compact source of radio emission, Sagittarius A star. All of this was discovered in the 1960s, 70s, and it was the beginning of the journey. Because on that scale, you can spatially resolve the gas, and you can hope to measure the motions of these gas clouds through Doppler effect. Basically, if you have line emission from these gas clouds, well, then the motion along the line of sight shifts the line into the red or blue, depending on whether it's moving towards you or away from you. So the radio source was observed numerous times with ever higher resolution by the radio astronomy community, especially with the technique of so-called intercontinental interferometry, VLBI, where you take telescopes nowadays spanning the entire globe and then interfering the light and then basically using the resolution, which then can be as good as a few tens of micro arc seconds. Remember, our eyes have a resolution of about 40 arc seconds, and normal optical telescopes have a resolution of about 1 arc second. This is micro arc seconds, so that's the equivalent of about a few centimeters on the moon. So with these kind of radio machines, you can actually resolve this radio source. I'll come back to this. But in any case, it's sort of a X marks the spot, because if there's such an intensely radiating radio source in the middle, compact, maybe that's the region around a possible black hole. And indeed, Charles Towns in Berkeley and his students, and I was then one of the postdocs who joined the group in the early 80s, began to map out these gas clouds, neutral and ionized gas clouds, and their motions. And from the motions of the gas clouds then inferred the distribution of mass as a function of distance from the center Sagittarius star. So Sagittarius star would be here on the left side. Note that this is a logarithmic scale in distance. 1 is 3 light years. And here's the mass, also in logarithmic units. You're very far away from Sagittarius star, then you see the mass changes with distance. gets ever bigger as you go away. That is an extended mass, and that's basically the entire nuclear star concentration. But if you come inside of about 1 parsec, and that's on this scale about this much, the mass does not change anymore. By 1985, we wrote a Nature paper in which we were proudly announcing there might be a black hole in the galactic center. But nobody believed us. Why didn't they believe me? The reason is that, number one, gas is not a very exact tracer of gravitation. You can push gas around also with other forces, magnetic fields, winds from stars, etc. More importantly, the point to which we could measure, which is here a few arc seconds, is equivalent to 1,000,000 times the event horizon size of a few million solar mass black hole. So most people said, well, okay, maybe it's a black hole, maybe not. I mean, maybe there's something else hiding. There could be a cluster of very faint stars, or stellar black holes, or neutron stars, whatever. So go back to the drawing board and work a little harder. That was the message which we got. And indeed, we did. How did we do that? Well, first of all, use the stars, not the gas, because the stars are a much, much better and reliable tracer of gravity. And the next thing is, of course, resolution. And you will see that the 40 years was basically sort of a pace by pace, phase by phase approach to get ever closer to the central region. In the first phase, we used a technique called speckle imaging to overcome the Earth atmosphere. The Earth atmosphere, as you know, when you look at a distant car coming you on a hot summer day, the air flimmers. And that, of course, destroys the sharpness of optical images. So in order to overcome this, you have to have a very good detector and overcome the scintillation of the atmosphere by taking very many short exposure images. That was known at the time, and so that we did. But the problem was, in the galactic center, you cannot use optical emission because the optical light is dimmed by what you saw in that movie, perhaps, these darkish regions, which are dust clouds, interstellar dust clouds, which dim the light by about a factor of 10 to the 12. No, we had to go into longer wavelengths, infrared waves, about 4, 6 times the optical wavelengths. And at the time we started, actually, there were no good detectors. And that was one of the technology developments which had to be done. It was done initially in the US by the military, and then came over to the civilian sector. Here in Europe, for instance, in France, it actually was done within the research community. Nowadays, we build very fancy avalanche detectors which overcome any noise source you wish from developments within, in fact, ESO and the research institutions. But it took a long time to get there. And then the next step was adaptive optics. So again, here's light coming from a distant star onto a telescope, and it's, as you see, the light waves are bent and tortured by the Earth's atmosphere, such that what was a very sharp image, when it is then recorded in the detector, gets unsharp by this so-called seeing. And the limit is, as I said, 1 to 2 arc seconds. But if you have a device in the path where you measure these distortions, and then you have a deformable mirror to undo what the Earth's atmosphere does, then you can make the image sharp, as you see on the left side there. Yeah, this is the speckle. This is the seeing limited image, and then when you switch on the AO, you get this very sharp diffraction limited ring. So on a 4-meter telescope, a 4-meter class telescope, that's about 1/10 of an arc second, and on an 8-meter, 10-meter class telescope, that's 50 milliarc seconds. So that was a huge first step. Nowadays, in fact, optical observatories are not anymore dark. We throw laser beams all over the place. Why? Because in order to do this adaptive optics correction, you have to have a pretty bright star very close to the science object, and that's rarely the case. So make your own star. So you shoot a laser in the upper atmosphere and scatter there. There's some sodium atoms in the upper atmosphere, 90 kilometers height, and use resonant backscattering to then basically have a constructed beam of something which then from below looks like a star, but you can place it anywhere you like, of course. So this technique is now a standard and allows all telescopes to be sharp. In fact, the ELT, which is 5 times as large, will only work with such lasers, not only one, but actually 4 or 5 in order to get that correction. There are many other tricks which we had to invent or develop over time. For instance, as you will see, for interferometric applications, we need to split the light very efficiently and bring it together. That we do in integrated optics. We use monomode fibers. The whole plethora of modern technology was at the core of the kind of work which I'm describing to you here. Now, in the first phase, we were looking for motions, just motions on the sky, proper motions as they are called. There was us and my colleagues in using a 3.5 meter telescope of ESO, but then we were joined by Andrea Guess and her colleagues using the then just beginning Keck telescope, 10-meter telescope. It was the first large telescope coming into operation in the mid-1990s. And both groups started working on this project, taking pictures and taking again pictures and again pictures and waiting over time. And you see here pictures of the central region. This is a light month here, half an arc second. In 3 different years, in red, in green, and in blue. And obviously, you see near Sagittarius star, which is this green cross, you see some stars having different positions in different years. And that is clearly a motion, and that motion is large, 100 times as fast as the Earth around the sun for this particular star. And you see there are many such stars, but you also see as you go out, the color is lost. The stars are getting white. What does that mean? It means the motion is small. That's Keplerian motion in action, okay? Keplerian motion. So there is a central point mass, and if you calculate v squared r over g, what do you get? Well, you get the same mass we had 10 years earlier from the gas clouds, but now people were willing to believe the measurement. Also, we are further in. Is it a black hole? We don't know, because this is still 100,000 times away from the event horizon. The same qualitative arguments that there might be something else which we hadn't figured out were still valid at that time. But some of the astronomy people said, that looks good. So what do you have to do to still do better? Well, bigger telescopes, and Andrea had that. We were then getting onto the VLT and adaptive optics. And then the next thing is luck. You need nature to help you. See, as a laboratory physicist, you can always construct a better experiment by yourself. Here, sometimes you need nature to help you. What do we need nature for? To give us stars which come much closer to the center than we had seen. That's not very likely. In fact, if we would have had to write a proposal, so to speak, please, we would like to build this, give us money. They wouldn't have given us money because it's so unlikely, but it exists. And both groups in 2002 found a star, which at that point, it was known from the measurements. We had seen it for 6 years. And then all of a sudden, the star in 2002 took the turn. Dramatic. Within a few months, it went around Sagittarius star with a speed of about 3% the speed of light and moving at a distance of only 16 light hours. That's about 3 times Neptune's orbital radius. That's about 1,100 event horizon sizes. So 100 times deeper than what we had seen before. And so that star, which we now have seen, as you will see further, twice going around this region, is our best probe of gravity in the central region. but we still have to do better. We have to do better if we want to see the deviations, the predicted deviations from Newtonian motion due to general relativity. So in 2005, we thought, well, what can we do to get a bigger telescope? We cannot build a 100-meter telescope. Yes, we can. I came out of radio astronomy, so I knew about interferometry. You take the 4 8-meter telescopes on the mountain in Chile, which you see there, and connect them together through delay lines and mirrors and everything, and bring the light together below the plane there. So that's how the VLTI works. You have 4 telescopes with an effective separation of 130 meters, and then you bring the light down the Coude trains, many mirrors, unfortunately, and then you bring the light together in a beam combination laboratory where we developed a beam combination instrument, a cryogenic instrument with fibers and mirrors and whatever else have you, very complicated machine. We send lasers throughout the whole system to measure distances, et cetera, et cetera. Very, very complicated development. Took 10 years to build it. Frank Eisenhower is the leader of that very complex experiment, which many people felt could not be done, but it did. It did. And we knew the star, which you've seen, will come back. 16 years. We knew the date was May 2018. So we've got to be ready to see it coming back, because the effects of general relativity depend strongly on from the distance of the mass. Since this is a highly elliptical orbit, most of the effects can only be seen near Perry. And indeed, that's what we did. That's the current state. Not only did we see S2, this star, go through Perry, we saw the motions there, not anymore from year to year, or month to month, as we did previously. No, from day to day. 7,700 kilometers per second. And it parried exactly on the 18th of May. And we know all the parameters of this system mathematically to many digits. This is a precision physics experiment. And we also can measure the velocities of the star with high precision. So the whole system is extremely well characterized. And not only that star, we are now following a whole bunch of stars with the interferometric technique, as well as the adaptive optics technique. And here again, that's what we saw in 21, just to give you a feeling over a few months. In the center there, that's Sagittarius star. And then you can see how all of a sudden several stars in 1 year parry with very high speed. You can also see down there, that's Neptune's orbit. You can see how close these stars come to the center. And that's the trick. That broke the ice to measure, now the mass and the properties of the physics in this region, which really tests general relativity and is a real test of the black hole proposal. So we know the mass now to 0.2%, and the distance likewise. We know that any extended mass around the black hole on the scale of this S2 orbit is less than 6,000 solar masses. Compare that to 4 million. So that region around it is empty. I'll come back to this. Very important astrophysical constraint. Now, as to general relativity, the first effect one would expect is the fact that Einstein's theory predicts that if you have a mass going around another mass and sending out light, then the light has to escape that potential. And that leads to clocks going slower or light getting redshifted. So this gravitational redshift is a quantity which is very well known. And in the galactic center for that orbit S2 is an amplitude of about 200 kilometers per second. Note that this is only about a few by 10⁻⁴ of the orbital velocity. So you have to measure pretty damn accurately. And we see, that's Newton down there, and the GR prediction is the red curve. And you can see that the measurements clearly are on the red curve, and the fudge factor, so to speak, we can derive from this mathematically is this F factor where F equals 0 is Newton and F equals 1 is general relativity. And you see that's a 27 sigma detection of the gravitational redshift. So that's pretty damn good. But there's a next even more interesting set of measurements one can make, and that's the so-called precessions. So if you have a Newton system, and if you have a star or a planet orbiting, oops, oh nice. Always, it's a pleasure to get mail. It's okay. It's okay. No, don't touch anything.
We would like to remove the bar. No, no, it's okay.
So look on the movie on the left side. So there you have a star around a black hole, if you like, on an elliptical orbit. So in Newton, that elliptical orbit would be always in the same direction and same orientation for all times if there's no perturber around. Not so in general relativity. In general relativity, there will be two precessions. One is in plane, the so-called Schwarzschild precession, prograde. And the other one is if the central black hole has a spin, then there's also a wobbling of the orbit around the spin of the black hole. In mathematical terms, the more easier one to detect is a Schwarzschild precession. The spin precession, the lens-tearing precession, is much more difficult. In the case of the galactic center, about 50 times more difficult. We have not yet seen it. But when you make these measurements, you can do the same I showed before. You can fit to this data a Keplerian orbit, a Newtonian orbit, and then calculate the residuals in X and Y. That's what you see here. So a Keplerian orbit would always stay in one position in this residual plane at 0, 0. Now, if you go to GR, then that's what you should see. A very complicated set of residuals due to the precession. And you can see that this has a lot to do with what the 0 point is. In our case, we nulled the angles at the apo, the most distant position, in 2010, which is up here. So that's this point here. And then you can see these loops which happen around Paris. So there's the first Paris we saw in 2002, and then the second in 2018. The next apo is in 2026. So these orbits loop all around. What do we see? That's what we see. Not bad for government work, I would say. And so if you have the same fudge factor, we now see this Schwarzschild precession, which is a much tougher cookie to measure, actually, with about 12 sigma accuracy. That is astrophysically extremely interesting, because if you have any perturber around, another mass or set of masses, that would not be the answer anymore. If you have another mass, then immediately there would be a so-called Newtonian retrograde precession. And that could, depending on the mass, destroy this pattern. So by seeing the pattern so clearly, we immediately know that the region around the black hole is fairly rarefied. In fact, we can do this through Monte Carlo Bayesian techniques and ask the question, given the observations, how likely and in what position and orbit could there be a second object of some mass? And this is shown in this weird looking figure here. This is mass of a second object, 2,000, 4,000, 6,000. And this is the distance around Sagittarius star. And basically the Monte Carlo analysis shows you that, yes, you can, in principle, put something inside of the orbit of S2 as long as it's less than 2,000 solar masses. So that means, for instance, that this black hole is a loner. Many people, theoreticians and observers alike from AGN work, had predicted that big black holes might very well be surrounded by intermediate mass black holes, apparently not in the galactic center. And we can say this to a pretty astounding degree of accuracy now. Of course, there could be stellar black holes, and they would be expected, and they might show up at one point. How? Well, through a three-body interaction between one of these stars we're observing, S2, and one of these stellar black holes. What happens then? Havoc. If a stellar black hole would come close to S2, S2 might very well get ejected out of the system in a hurry. So if that happens, it could be drastic, but we haven't seen it yet. Okay, so far, we've made precision measurements, but still at 1,000 Schwarzschild radii, 1,000 times event horizon. Can we not get closer? Can we get to the near event horizon regime? And that is the regime of Sagittarius A star itself. And the answer is yes, both with methods of radio astronomy, you will see, and then with the infrared measurements. And that is because Sag A star is visible in the infrared as well as the radio. There is the trace over time of how Sag A star emits in the infrared. It's highly variable, continuously variable, with amplitudes up to a factor of 30 or so. It's also variable in X-rays, by the way, with even more amplitude. So if you observe Sag A star and you're patient, you will see an eruption of substantial size almost every day, maybe 2 days. So that's interesting. What are these eruptions? Well, if you look at the spectral domain, the quiet emission from Sag A star is a synchrotron emission peaking in the millimeter, sub-millimeter regime. That's synchrotron emission from very hot gas, about 10 to the 11 degrees, and magnetic fields of around 100 Gauss. Then there's a little bit of X-ray emission, which could be also due to synchrotron emission, or other emissions which have to do with very hot gas. But then, as I said, once per day, there's an eruption, and that takes mainly place in the infrared to X-rays. We are sure from polarization measurements that the infrared emission is also synchrotron emission. In the X-rays, there's a debate. Most people feel these days it's also X-ray emission, it's also synchrotron emission, but it could also be Compton scattering. So what are we seeing here? Most people feel what you're seeing here are events which we are very familiar with on the sun. Magnetic structures, in the case of the sun, these are loops, which from time to time bang into each other, release energy and accelerate electrons at the tipping point where they bang into each other. And these electrons run around in the sun, these loops, and bang against the surface of the sun, thereby releasing a flare of emission. So maybe the galactic center structures are similar. You have a highly magnetized plasma, and they bang into each other, and then that generates accelerations of some fraction of the electrons, and they make then all of a sudden infrared emission and synchrotron emission, which then, however, cools again, and so that's why you get this characteristic shape here into the X-rays. So that's the picture. Hotspots. And if there's a hotspot, and it might move around the center. And indeed, we saw that early on, and in fact, by now we've seen about 5 or so so-called astrometric flares, where what you see here is the position of the Sag A star emission from in the infrared as a function of time on the sky, and its flux. And you can see there's always sort of a loop type structure. In fact, the loop type structure is always in the same direction in time, always clockwise over all these years. At the same time, we can measure the polarization of this emission. It's also loopy. So this is the polarization in one direction, and that's in the perpendicular direction. And you see loop, loop. So when you have that, that tells you have a fairly, repeating a process of something which does always the same thing. So what you can do then is you can add these very noisy things together to then get actually information on the average property. And all of a sudden you see on the astrometric signature in X and Y, very characteristic loop motions, and in polarization, the same thing. So on the sky, the average motion is like this, clockwise, and the polarization pattern also. Or if you put the polarization pattern on the orbital pattern, you see that basically you have a magnetized source which loops around in space and in magnetic field structure. So that's a very regular thing. And that you can use to now calculate a number of interesting properties. The first property is the orbital time. It's just the time that you take to go once around. And both for the polarization and the astrometric flares, that's about 60 minutes. The next is the radius. Well, that depends, of course, on the orientation of this motion and whether it's a circle or not. Let's assume it's a circular orbit. Then this radius is 8 Rg, or 4 Schwarzschild radii. That's very close to the so-called innermost stable orbit. General relativity predicts that when you have particles moving around the black hole, it can do so, but no only to an innermost orbit, which is about 6 Rg, not 8.2, 6 Rg, or 3 Schwarzschild radii for a stationary black hole. So this is pretty close to this ISCO. For photons, it's about 1.5 times the Schwarzschild radius. So inside, the photons can orbit a little further in. We can also determine the inclination. 150 degrees means this plane we are looking at is only 30 degrees off face on. So you will see what that means. That gives you a very important constraint on the inclination. So you can use all of this and do a global MC fit. If that is gravitational motion, then we can measure the mass. But now at 8 Rg. And what comes out is 4.8 plus minus 1.8. Not bad for government work. Next, photons. Let's play with photons. So if you look at a black hole, there it is. And here we're looking from the left. And if there's a light source in behind, which is illuminating this entire plane here, then in GR, the photons which come here towards the black hole, of course, disappear in the black hole, like they would be in a star in Euclidean geometry. But in GR, also photons which in principle make it outside fall in because of the light bending. And in fact, all the photons within about 2 Schwarzschild radii do not reach us. So when we look at this black hole and it's illuminated from the backside, what we should see is a dark region surrounded by a bright ring. That's the prediction. Now, of course, the source of illumination might not be, strictly speaking, a point source behind the black hole. So that there you have to be a little careful and evaluate other options. But this prediction for a point source says that this darkness, this shadow, should be about 10.2 Rg on the sky. 10.4 to 10.2 Rg is in the galactic center, because we know the mass, 2.2% accuracy, we think, 50 microarc seconds. So the prediction, the prior is, if you take a radio interferometer and point at this central source, you should see a dark region of 50 diameter, 50 microarc per second diameter. That's what our colleagues in radio interferometry, the EHD consortium, has published last year. 51 plus minus 2.3 microarc seconds. So you can turn this into a mass, and what you get is 4 plus minus 1.5 million solar masses. Not bad for government work. In fact, also this emission here is mostly face on. So if you plot here the inclination and the radius, then the flares we are seeing coming from this region, but they are, pretty much near face on, and so is the radio emission. So we know the orientation of everything. Why is that orientation business interesting? Because it teaches us something about the orientation of the accreting gas and perhaps about the spin of the black hole. Now, there is a so-called Bardeen-Peterson effect. If the black hole has a spin, then if gas streams in from some direction which is not identical with the plane of the spin, it will be forced into the orbit as it nears the black hole. This Bodine-Peterson effect therefore says, if that is applicable to your black hole, then all the gas very close to the black hole should be in the plane of the spin, or the perpendicular to the spin of the black hole. That would be, that's nice, isn't it? Well, there's one problem. If the density of the gas is not sufficient to do this force, well, then you would not see the spin plane, but you would see the plane of the gas, of the source which provides the gas from the outside. Okay? So let's look at the galactic center. Let's then define here the plane here of the innermost region where we're seeing gas going around. Then we have magnetic field strength, which is at an angle theta relative to the line of sight. And the most likely direction of the magnetic field in these hotspots, you would think, is in the plane of the orbits, in the plane of the motion. That's called a toroidal field. If you have a toroidal field and you look at this from above, then you see that the direction in horizontal direction per orbit appear twice, and perpendicular also twice. That means, by definition, if you measure the polarization, per orbital period, you have two loops in polarization. We see one. And that means that the field direction in these hotspots must be more or less perpendicular to the orbital motion. That's a poloidal field. That's remarkable, because that can only be if the energy density in a magnetic field is larger than that in the gas, which is rarely expected in these kinds of systems. So that's what we can derive. Orbital period is equal to the polarization loop, means theta is small, poloidal field configuration, and that means it's the gas in the innermost region, the galactic center, is magnetically dominated. And we can actually make a ray tracing fit to the polarization patterns on the sky and in time, and then fit this with these kinds of parameters. And now finally, how is it oriented, this plane? Well, here's the sky, and everything above this line here, take this horizontal line here, everything above here is counterclockwise. Everything down here is counterclockwise. So everything here goes this way, everything here goes that way. The Milky Way plane is here. And then there are various other structures which you can see. Let's go straight to this. This here, up here, at fairly face-on clockwise, is the so-called plane of very powerful Owen Wolf-Rayet stars, which are surrounding the galactic center on scales of a few arc seconds. They are of great interest because these stars emit winds, very powerful winds of ionized gas, and they are feeding the galactic center. And our plane, which we are seeing at the event horizon, coincide within the measurement accuracy with the angular momentum direction of those disks further out. So we can say we are likely looking at the production mechanism of what goes into the galactic center right now. Are these stars, not the spin of the black hole, and the direction of the plane inside is not dictated by the black hole. So the density is low, and probably also that's done by these people, Ressler et al. Through simulations. The spin of the black hole is also probably low, because if it's large, then it also forces this Bodine-Peterson effect. Okay, after 40 years, we've come a long way. We started back then seeing just the onset of this flat mass as a function of distance from the center, which is characteristic of a point mass. In the 1990s, we were seeing stars out here And then we were beginning marching inward with the champion S2 being observed by both us and UCLA and found the same way, 4 million solar masses. But having the doubt that maybe there's something in between that and the event horizon, which is this black thing here, there could be, for instance, as many people speculate, dark matter, a spike of dark matter in the central region, which looks like a point mass on these scales, but is not a black hole. But with the measurement, which you have shown you, of the event horizon telescope and the flares, we now have a measurement point right near on the event horizon scales, the black hole, and it's the same mass. So we can probably pretty much forget about this, at least to the scale of a few thousand, more than a few thousand solar masses, which I've shown you is sort of the limit we can have. So, is it a black hole? I leave that to your judgment. Do we know the spin? No, we don't. So that's the next thing we would like to see, the lens steering position, and that will be a hard one. Whether I see that in my lifetime, I don't know. But there is a definite way where this might become possible. And that's gravitational waves. The so-called no-hair theorem of general relativity says that a black hole, at least an uncharged black hole, has only two properties you need to know. One is the spin, chi, and one is the mass, m. There are no hills and no ups and downs on the surface of a black hole gravitational field. And the quadrupole moment of a black hole is given by the spin and the mass, and any other higher moment is. So whilst for the Earth, you have to measure several hundreds of terms of higher order moments in order to determine the gravitational potential of the Earth, a black hole, very simple thing, two properties. And because that's the case, you can actually calculate nowadays the wave pattern, what happens if you have a massive black hole and another black hole falling into it. And that should be able to be measured through a mission which might be launched in 2040, the so-called LISA mission, sending laser beams between 3 spacecraft at a distance of about 2.5 million kilometers. And that measures the gravitational waves, a fairly low frequency, and that is exactly what you would need if you have a stellar black hole falling into a big black hole. And so the dream one might have is that one observes this process, which I'm sure you can't hear because we don't have an audio on, where you see as the stellar black hole inspirals into the big black hole, higher and higher frequency, and then when the two event horizons merge, end of show. End of show. Thank you.
Thank you so much, Reinhard. So, questions from the audience? Don't be shy or... I mean, you cannot compete, so there is no... Oh. No one? Ah, come on, I don't believe it. Roberto.
I think some attempt to report spin measurement for the black hole at the galactic center were made by the Event Horizon collaboration. What is your take?
No, I would say I mean, I showed you actually the dependencies there. What you would expect is that the shadow gets smaller a little, yeah, but that's degenerate with the inclination of the whole structure. Perhaps the most important effect is it gets asymmetric a little. I would say this is way beyond the current technique. This is unfortunate because, I mean, the Sergei star shadow is the largest of any known black hole, bigger than that one of M87. And in principle, it's the best source, but it's a relatively small black hole. And that means that the so-called dynamical time at the photon orbit, that's how long it takes for a photon to march around 1.5 to 2 times our Schwarzschild radius, is only 10 minutes. And that's at the core of these variations we see. So the benefit which we draw from the fact that the source is variable is a terrible thing for the radio astronomers, because they see the variations also. And that means the technique in radio astronomy in VLBI to make an image is to record the so-called fringes or visibilities and phases for, a number of hours, and then do a Fourier transform that you cannot do easily because the source structure has already changed. And so that was one of the biggest struggles. I mean, mind you that the M87 image came out 2019, this one in last year, yet the data were taken at the same time. So they struggled enormously to demonstrate or convince themselves that they actually had an image. And if you look at the precision of the shadow, is not very good. But, one can hope that if enough images in the future can be recorded, then you can do more of a Bayesian type analysis, which would overcome that. Let's see. Whether that goes to a spin, I'm not so sure.
In your opinion, to go even beyond the wonderful science on black hole you just showed in the future, would it make more sense to still target? Are we going to learn more targeting our own black hole, the one in the Milky Way, or to go beyond the more massive black hole in external galaxies would be a better target for some of the next science?
Both. I mean, certainly for the astrophysics part, the external galaxies are interesting because you want to understand a number of other issues, not physics issues, but universe issues. Who was the first? Who formed first, and when, and how? We know there are a number of very powerful black hole emitters, AGNs, now at redshift even 6 and 10. So that's only a few 100 million years after the Big Bang. If you have what we consider the maximum accretion rate onto a black hole, the Eddington rate, then the doubling time for the mass of a black hole is about 400 million years. So in this speed limit, so to speak, if you start with 1,000 solar masses, which is already a lot, then 400 million years, you have 2,000, then 4,000, and so forth. You can immediately calculate how long it will take you to go to several billion, which is what these black holes are, which are observed. And it's impossible to form them in the first billion years. So something must be wrong in our picture. Perhaps the speed limit is not correct. They're speeding out there in that the accretion goes in one plane and the photon pressure in the other, and so forth. So the external galaxies, in my view, is exciting because you will look at the cosmology of all of this. It's also exciting because you will, better understand the evolution, the mass distribution, et cetera, et cetera. With gravity, the instrument I've shown you, we are already now measuring precision masses of black holes at redshift 2.3. Undoubtedly, this will become an industry, because so far we've relied on scaling relations and measurements of so-called reverberation variations of the central region. But then the nearby black holes, you would think are the way to go into the subtle details in measuring these measurements of structures. And maybe we are lucky in seeing a star disrupted. Maybe we are lucky and see a star come so close that we see the lens tearing. I think one should try it all. It's fun, lots of fun.
Thanks.
Yeah, Roberto.
Can you hear? Yeah, yeah. Fantastic. And everything, the presentation, all the data, it's so exciting. I think a few years ago, I remember some announcement that there was a gas cloud, I think dubbed G2, that was approaching the black hole. And as for people working in the AGN community, it was super exciting because we would see the black hole in the Milky Way turning into an AGN. And I was wondering if there is a prediction or expectation of some of this happening in the
Thank you, Roberto. This is a very good question. I couldn't put everything in here. Okay, so yeah, about 10 years ago, we saw an object moving toward the galactic center in a fairly, almost parabolic orbit, ellipticity 0.95 or something like this, coming in, but then noticed that it was spatially resolved along the motion of the orbit. And that we saw in a line tracing ionized gas. So clearly we had to do with a gas cloud. At that time, there were a number of simulators, and which basically simulated that situation. We had some limits on the density of that gas cloud, et cetera, et cetera. So they simulated then what would happen if you have a gas cloud moving on such an orbit into the central region, going as close as, well, again, 1,000 Schwarzschild radii. And the answer was it would be disrupted, absolutely clearly disrupted through Kelvin-Helmholtz and Rayleigh-Taylor instabilities. And at that point, then basically you would circularize the gas, and it slowly would make its way inward. And on a time scale of 15 years, it would start raining onto the event horizon. You would see fireworks. And that was the average prediction. But then came some people and said, well, wait a second, you see an extended gas cloud for sure, which is tidally disrupting, but maybe there's a star there. And that's absolutely the case. We don't know whether there might be a faint little star in the center, whether that's a protostar or just a faint star, we don't know. So there were different opinions, but the gas story is very clear. And we saw, indeed, almost textbook-wise, that when the thing parried in 2014, it was almost 10 times as long as wide. So spaghetti, spaghettification was seen. And then it pulled itself back together again. That's what you would expect. If you have a tidal disruption, which is not leading to a destruction, then as long as you're in vacuum, you would expect, again, the cloud coming together with the exception of thermal motions. And that's a relatively small thing. That's what we've seen. And that has given us, the fact that we didn't see it disrupt, a very precise measurement on the density of the accretion flow at 1,000 Schwarzschild radii. Okay, that's part of the story which I sort of used in telling you that the gas energy density is lower at the event horizon than the magnetic one. And there's several others of these guys around. And this particular one actually is part of a whole stream. And the speculation had been in some of the theoretical community. What you might see is the remnant of a giant, which was tidal disrupted, and then gives you basically sort of a spray of material which comes back ever more. But I mean, it's certainly an interesting part of the story. It's just that is not relevant for trying to measure general relativity effects.
Yeah, Marcello.
So we know that even more massive black holes, like the one in M87, can launch relativistic jets. We also know that there are like these so-called Fermi bubbles around our own galaxy. So there might have been some activity from our black hole in the past. So what's really the driving parameter for creating a relativistic jet? Is just the mass or
Spin.
the environment?
It's the spin. I mean, at least I adhere strongly to Roger Blandford's interpretation of the story, which is it's the spin and black holes, which are most likely spewing out very clear jet emission, are those with near unity spin. Okay, and how do you get near unity spin? You get it if you accrete at near Eddington for quite a long period of time, actually. So if you start with a zero spin object and you calculate how long does it take to spin it up through accretion, then you have two conditions. One is the angular momentum of the stuff coming in has to be always the same. And the next one is it has to be near Eddington. Neither of the two is true for the galactic center right now. The stuff which is coming in, for instance, these stars, have nothing to do with the Milky Way. In fact, you've seen the Milky Way angular momentum was somewhere completely differently. And the next thing, the m dot into the event horizon in the galactic center, on average currently, is 10 to minus 8 solar masses per year, where Eddington is 10 or so. Yeah, so we are hopelessly hungry, starved, or whatever you want to call it that. But then, is there evidence that it was different in the past? Yes, there is evidence from X-ray scattering, which you can interpret that a few hundred to 1,000 years ago, the rate was, I don't know, what is it, 1,000 times bigger or something like this than now? Is that near Eddington? No, it is not. So my suspicion is that the galactic center is just a late bloomer in a universe which is dying out. Yeah, well, the hefty ones have been fed well at a much more profitable time, so to speak, and thereby you can do these jets. But anyhow, I mean, this is my interpretation. I'm sure there are others. If you take the other version of Roger Blandford's work, where you have a disk wind leading to a jet, then you could also do it from the accretion flow, and not just from the innermost rotation to the black hole magnetosphere.
Leonardo?
Let's pretend that I am a master student. And I've looked at this beautiful talk, this beautiful voyage that you have basically devised through your career. What would be your recommendation to a master student to develop his life in astrophysics?
Oh my. Ay, Leonardo. I'm not sure I want to answer that. I actually would go into neuroscience. So, but what I'm telling you, for the kind of taste I have, these world observatories, where if you're lucky, you might get 3 hours of observing time after 10 applications. It's not my science. It's not my science, because, if you put an entire group like ours, and we're lucky to have such a group, for years to develop such an instrument, and then you don't get guaranteed time, as many people want. You know ESO, right? There's many people within ESO who now say, no, let's not have none of this would have been possible without guaranteed time. And while the big observatories all know, HST and otherwise, that their most lasting and biggest and splashy science comes from the big programs. At the level of the community, you tell everyone they should become independent, self-agent of 2 hours of ALMA time. No. And if that's the condition which we want to now live on, I better go into neuroscience. I apologize for this slightly arrogant comment.
All right, I think we can close. Okay, yes, let me thank the seminar crew, Fabio, Elisabetta, Tatiana, Enrico, and the assistants from Alessandro and Renato that made the event possible. You all that come to the seminar, and Reinhard Genzel for his beautiful talk. Reinhard will be here in the afternoon, I don't know, till some hour in my office at the Battiferro, and maybe also a few hours tomorrow morning, we don't know. So if you have more question or a selfie, you can come. Don't be. Thank you.